So we started yesterday, 4.2. Okay, we looked at some graphs where we had horizontal and vertical asymptotes. And we were looking at what are called rational functions. There's one thing I want to mention about rational functions, and it's something we've done before. And it would be these different boxes. Each one of these boxes would do something to the rational function. Either shift it up and down, shift it left and right, or stretch it up and down. The first one I want to look at is this one. Adding and subtracting a number in the bottom of my fraction. This is adding and subtracting inside the fraction. Does anyone have an idea what that would do to my graph if we add or subtract inside the fraction? How about adding and subtracting in general? What does that do to a graph when we add or subtract numbers to it, either inside or outside at the end? Yeah? It's fine. So can you say it again?
Like it like changes it like where it's at and where it continues to go, so it changes the size of it?
Let's think about this one. If we put a +3 on the end of a quadratic function like that, what would that +3 do? You remember? +3? What'd you say?
Would that be where the line intersects the y-axis?
So we're looking at adding or subtracting inside the fraction. So what would a number in that box do?
Move it left or right.
It would shift it left or right. So this is a shift left or right. If it's a positive number, it's going to move left. Negative is going to move right. Okay, now, here. That's still adding or subtracting, but this time it's outside. Outside what? Outside the fraction. Outside the parentheses being squared. Whatever your thing is, it's outside. What does adding and subtracting on the outside do? Yep.
Move it up or down.
It moves it which way?
Up or down.
Up or down. Yep. So this is a shift. Up or down. Positive is up, which is what you would expect. Negative is down. So adding and subtracting is a shift. This is multiplying by a number in front. Same idea as this. Multiplying by a 3 does something to the graph because it's multiplying in front. What does multiplying by a number in front do? Yeah? Which way? Vertical. So when you have a function and you put a number in front of it, it will cause to either stretch or shrink vertical. When does it stretch? If you multiply by a number in front that's bigger than 1. When does it shrink? If you multiply by a fraction, like 0.5, 0.6, something like that. So this is a vertical stretch. Now, what if this had a negative in it too? it causes a reflection. So negative causes a reflection. And what axis would that be over? The x. Okay, so just go back here for a second. Remember, when you put a negative in front, it causes the graph to reflect over the x-axis. So there's basically up to 4 things that you could see happen in a graph. You could shift it horizontally, you could shift it vertically, you could stretch it, and you could flip it. That's the 4 things we could see happen. So if I gave you a problem like this, 1 over x minus 3 plus 2. And I said to you, tell me what's happening in that graph. There's a certain order you have to describe these transformations in. And we talked about that order as well. Okay, this is from 1.5. You always start with any horizontal shifts, then your vertical stretches, then reflections, then vertical shifts. So let's see what we've done. About, let's see, grade. Do we have any horizontal shifts in this problem?
Yes.
We do. What number tells you the horizontal shift?
The -3.
The -3. And can you tell me which way it's going to go?
To the right.
It's going to go to the right. Yep. So shift right 3. And second transformation, well, it's the only other number we have there. It's plus 2. What's the plus 2 going to do? Yep.
Shift up.
How many? Yep. Shift up 2. So I know it's been a little while since we talked about transformations like that, but it's still the same rules that we learned, and it's the same rules for every single function we study all year. We haven't really studied square roots a lot yet, but I'm hoping you could guess what that plus 4 would do to the square root. It's a plus 4 inside. It would shift it to the left 4. Yeah.
Can you bring up that other page that had like the 4 steps?
The 4, yeah. So you can also get it if you go back to section 1.5, which was on the 19th. Okay, so that's in general how transformations work on what we call rational functions. Look for a number in this box, and that box. And I've labeled what each one of them will do. You won't necessarily have every single number in every single problem. Yeah. All right, so that's something I wanted to just remind you about, because you might see something with a problem like this on the test tomorrow, just like the one we just did. All right, so the last part of what we're going to look at is graphing. And the type of graphing we did yesterday, the degree in the top was always bigger or equal to what was in the bottom. So we might have graphed something like this. So the degree in the top was bigger in that case, or we also looked at it when it was equal. I'm sorry, that was smaller, so I should do it the other way. That's what we looked at yesterday. The degree in the bottom was smaller than what was in the top, or it could have been equal. Now we're going to look at what happens, actually, when I had it the other way, where the number in the top is bigger. Okay. When the number in the top is bigger, something a little different can happen. Okay, but that's what we're going to look at. Now, the more, how can I say it? The further apart the degrees in the top and the bottom, the more complicated it's going to be to draw. So like, if you had something like this, not bad. The degree in the top is a 2, the degree in the bottom is a 1. That's a difference of how much? Just 1. Okay, so that's pretty straightforward. If you had something like this, the degree in the top is a 4. What's the degree in the bottom? 1. What's the difference? 3. That's going to be a little complicated. The bigger the difference between the top and the bottom, the worse it's going to get. Okay, we're going to mostly focus on where the degree is only 1 different. Not 2 different, or 3 different, or 4 different. Just 1 different. Okay, because then it starts to get harder after that. All right, so what we can end up with when we have a degree in the top that's bigger is something we didn't talk about yesterday. This is called an EBA. It's an end behavior asymptote. This thing doesn't exist for the types of problems we did yesterday. It can only happen when the degree in the top is greater than the bottom. That's the only time it can happen. So let's say I gave you a problem. An example problem is going to look something like this. You'll have a polynomial on the top, and you'll have another one in the bottom. If we divided these two things out, okay, we talked about how to do that on Monday. We did long division. When you divide something out, what do you call the answer when you divide two numbers? It's called the quotient. So when you divide, you get a quotient, and what's the other thing you get? You get a remainder. In order to find what's called the end behavior asymptote, I'm going to write it this way. So, if you divide h of x and g of x, if you divide them out, you will get a quotient and a remainder. The quotient is called the EBA. So there isn't anything new to learn. If you know how to do division, you already know how to do the EBA. We just never called it that before. But the quotient is the EBA. So the way you find an EBA is what we learned on Monday. You do the long division, write down the quotient, and that's it. That's all you have to do. Let's try an example. So here's a problem, and it says to find the quotient, find the remainder, and find the EBA. All right, so let's start with dividing that out and see what we get. This is not one we would sketch, because the degree in the top is a 3, the degree in the bottom is a 1. That's a difference of 2. I told you we weren't going to do a difference of 2. So we're not going to actually sketch this problem. Just want to find the EVA. Alright, so Austin, what's my first step to do this division?
You have to multiply.
That's the first letter of each step. So we are going to multiply, but that's not till the second step. The first step is to divide something.
2x by 2x to the third.
So take 2x to the third and divide it by what?
X minus 2.
Just the x. Okay, so take 2x to the third and divide it by the x. So if you want, you can do it off to the side. And when I divide 2x to the third by x, what do I get? Same.
2x to the second.
Yep, 2x to the second. So there's the divide. Now we multiply. Multiply it back out. 2x squared times 2x. And 2x squared times negative 2. That's negative 4x squared. So there's that step. What's the next step after multiplying?
You're going to subtract.
We're going to subtract. If you've done this right, something should cancel right now.
They both should cancel.
2x cubed minus 2x cubed. Oh. Negative 4x squared minus negative 4x squared. That also cancels. Whenever that happens, that doesn't always have to happen, but if it does happen, that means we're now done. So that sped things up. So now, we did the subtraction. The next step would be to bring down your next term, but the degree on this is a 0, because there's no letter. The degree on this is a 1. This is now smaller than that, so we're done. Okay. So let's write down our quotient. What's my quotient in this problem? 2x squared. What's my remainder? 3. And what's my EVA? 2x squared. The EVA and the quotient are the same thing. There you go. And that's it. We're not going to sketch it. That's all I wanted to do. Any question on that one? So let's summarize a couple things, and then we'll try to sketch. There's a difference between an EBM and an EBA. EBM is what we learned yesterday. EBM is simple. To find an EBM, all you do is take the highest degree term in the top and divide it by the highest degree term. Did you sign it back in for me again? All right. Divide by the highest degree term in the bottom. EBM, very simple. EBA, a little bit more complicated. You have to do long division. So that's the difference. When you're looking at a problem, sometimes the EBM and the EBA come out the same. Sometimes they don't. It depends on the problem. But in general, we're going to be finding EBAs when you have problems like this. When the degree in the top is larger than what's in the bottom. That's generally when this applies. EBM is when the number in the bottom is bigger. And that's what we did yesterday. Now, yesterday, remember the kinds of asymptotes we had? What were the two kinds of asymptotes we studied yesterday? Yeah?
Vertical and horizontal.
Vertical and horizontal. The point there, vertical is a straight line. Horizontal is a straight line. And you will always have asymptotes that are straight lines when you do the kinds of problems we did yesterday. Now, if that's not true, if the degree in the top is bigger, what can start to happen is you can get an asymptote that curves. The more the difference between the top and the bottom, the worse the curve is going to get. That's why I told you we're not going to look at ones that have any more of a difference than 1 between the top and the bottom. So if I had something like x to the 5th and a bunch of stuff, then I had an x cubed and a bunch of stuff. What's the difference between the degree in the top and the bottom there? 2. That's a difference of 2. And what shape is the graph of something that has an exponent of a 2? Yeah, it's a parabola. So what you could get, if we were to try to graph a problem like that, would be something like this. You could have an asymptote that's a parabola, and your graph might look something like this. And what happens is the graph continues to get, it's like it wraps around that parabola. The graph continues to get closer and closer and closer to the parabola. Most of the time, we had something like this. A nice straight line, and the graph would get closer and closer and closer to something that was a straight line. Well, this is getting closer and closer to something that curves. So that starts to get a little complicated, which is why we're not going to look at ones that have a difference of degree 2. We're going to look at ones that have a difference of degree 1, and we'll see what happens. Same general idea is going to apply when we sketch. If you can find the intercepts, we'll do that. Try to find the vertical asymptotes. And then we're going to use the calculator to help us. All right, so what I want to do now is I want to graph, where is the problem we just did? I want to graph this problem, and I want to graph what we think the EBA was, 2x squared. And I want to show you that when you graph it, this is going to be a curve that it gets closer to. All right, so let's see what it looks like. So whenever you type in a fraction, always put it in parentheses. So 2x cubed minus 4x squared plus 3 and divided by x minus 2. Now graph the EBA, 2x squared. And I'll try zoom 6. I might have to adjust it. Let's see what happens. Yeah, I need to set my y max higher. So I'm gonna take my window and set your y max to like, I don't know, probably like 30. Oh, that's x max. Let's try 30. All right, so what you see in blue, that's the actual graph. What you see in red is an asymptote. The idea is the blue one and the red one should be getting closer and closer. Let's see. So if you look at that, Can people see how the blue graph, which is the real graph, and this red thing, which is the asymptote, how the blue and the red are getting closer and closer? So the blue graph is getting closer and closer to something that curves. That can only happen when the degree in the top is bigger. So it's kind of weird. The blue graph, it's almost like a parabola, but it can't connect, so it kind of does something weird. We're going to take a look at sketching something. It's going to be a little simpler than that. Let's try this one. So it says determine the end behavior asymptote, the vertical asymptote, and then make a sketch. What type of asymptote doesn't it say to find that we found before? Yeah? Horizontal. You will not have horizontals. When the degree in the top is bigger, there are no horizontal asymptotes. Doesn't work that way. When the degree in the bottom is bigger, yes, there are. When the degrees are the same, yes, there are. But when the degree in the top is bigger, no. What's the difference between the degree in the top and the degree in the bottom? One. Okay, what is the degree in the top? Three. What's the degree in the bottom? Two. What's the difference? One. So this isn't as bad as the one I just showed you. The difference in that one was a difference of 2. This is a difference of 1. And that's the kind of problem we told you we were going to do. So let's find the EDA. How do I find the EDA for that problem? What do I have to do? Division. Divide it up. And because they're only 1 apart, the division isn't going to take very long. The further apart these numbers are, the worse it gets. But they're only 1. So we've got, I'm going to try to squeeze it over here. X squared plus 2x minus 3. And we're going to divide that into 2x cubed plus 7x squared. Remember, that part might not remember that, but you need to fill in a 0 for the x because you don't have it. Anything that's missing, fill in a 0. And then minus 8. Okay. So let's start by dividing x squared into 2x cubed. Ryan, what do you get if you divide x squared into 2x cubed?
2x.
Yep, 2x. Multiply it back out. That's going to give me 2x cubed. 2x times 2x is how much, Curtis?
4x squared.
Good. 4x squared. Dominic, what's 2x times negative 3? Yep, negative 6x. And what do we do with those columns? Subtract. 2x cubed minus 2x cubed is gone. Kiana, what's 7x squared minus 4x squared? 3x squared. And 0 minus 6 plus 6. And bring down the 4. And now we're at the last step because these exponents are now the same. Remember, when we're looking for the EDA, do we care about the quotient or the remainder? The quotient. So once I get the next number that goes right here, I'm done. I don't have to multiply it back out and finish it to get the remainder. All I need to get to is the quotient. So now, divide 3x squared by x squared. And what do you got? 3. 2x plus 3 is the quotient. You don't need to finish that off and get the remainder. You don't need it. That is my EDA, 2x plus 3. Now, so it's a little bit more complicated asymptote than we've drawn before, but what does 2x plus 3 look like if you graph it? It's still linear, but is it horizontal? No. It has a slope, and it has a y-intercept. So this asymptote is going to be on a slant, right? And it's called a slant asymptote. So it's one step more complicated than horizontal, but it still isn't complicated enough that it starts curved. It's on a slant. So let's put it in. What's my y-intercept? Okay.
That would be 3.
3. So we're going to put a dot on 3. And how do I use my slope to get another point? Yep.
Would it be up to over 1?
Up to which way is over?
To the right.
To the right. So I'm going to do that as many times as I can. I can go back the other way if I want to. And put in a dotted line. That's okay. Just put in a dotted line like that. And it keeps going. Okay, so that's the first thing we want to do. Put in our asymptote for the EDA, and then put in the vertical asymptotes. Well, the vertical asymptotes are where what happens? How do we find vertical asymptotes? Right, where the bottom equals 0. What can we do to make the bottom simpler so we can find the zeros quicker? Yep. Let's see if we can factor it. So if we try to factor it, we would need an x and an x. And what about two numbers that multiply to give me 3? 1 and 3, so I definitely need a 1 and a 3. And our signs have to be one of each. We need a plus and a minus. Where should I put the plus? Put the plus on the 3, I agree. That is how it would factor. So, where is one of my vertical asymptotes? Although, Paige, you tell me where one of my asymptotes would be?
1.
Yep. So let's put a dotted line on 1. And where would my other one be? Yeah. Negative 3. So let's put one at negative 3. So if you look at the pattern, it's very similar to the pattern we had yesterday. We had 2 verticals yesterday, and then we had a horizontal. Well, now we have 2 verticals, and we have one on a slant. So what we'll do is use the calculator now and plot some different points to see what this graph looks like. Okay, how many points? However many you want. If you need 50 points to graph it, then do 50 points. I could probably do it with about 6. That'll give me enough of an idea of what's going on. The quickest way to get points, besides just plugging numbers in for x and doing this out every time, is just use a table. So let's put that in. So if you have anything else, just clear it out. Let's put in 2x cubed plus 7x squared minus 4. And we're going to divide that by x squared plus 2x. Minus 3. I don't have to, but I'm just going to clear the numbers I already had in my table. So I'm going to start over. And Abigail, what would be a good number to plug in for x?
Which one do you
We're trying to graph f of x. Sure, we could try 0. So if we plug in 0, we get the point 0, 1.3. Okay, so there's a point. 0. I'll make it bigger so you can see it again. 0, 1.3. That's good. That's 1 point, but I need more than that. What would be another good x value to plug in? Yep.
2.
2. All right, let's try 2. 2, 8. Okay, so when I go right 2, I'm up at 1, 2, 3, 4, 5, 6, 7, 8. I'm up there. Okay, what would be another good one?
-4.
All right, let's try -4. -4 is a point. 1, 2, 3, 4. 1, 2, 3, 4. Okay. How about another good one? Yep. 2. So we got that one. 2, 8. You want to do -2? Okay. -2 is -2.7, roughly. So -2, -1, -2, -1, -2.7, about right there. Okay. Should always do a point near the asymptotes. Nobody said that yet, like we did yesterday. I want to check a number extremely close to the asymptote. So what would be a number that I could check that's extremely close to one of those asymptotes? 1.001. 1,254. So when you are just a little bit past 1, you are way up there. What would be a value that's just a little bit smaller than 1? All right, let's try 0.999. -1,245. So if you're just before the number 1, you are way down here. Let's check our other asymptote, -3. Give me a number a little bit bigger than -3. What is it? Negative 3. That's smaller. All right, so -2.999, just a little bit bigger than -3. And we are up at, well, we're down, -1,200 something. So we are way down there. And what about a value that's just a little bit smaller than -3? -3.001. We're up at 1,246, way up. Okay, way up. So way up here. So this graph is going to be in 3 separate pieces. Remember, as you sketch the graph, you have to stay as close as you can to the dotted lines, but in general, we don't want to cross them. So let's start with this piece. It's going to stay as close as it can to that dotted line, but it can't keep going down. It gets deflected by that other asymptote, and it starts to bend that way. Now, the section in the middle, we got the most amount of points for that one. It has to stay very close to all 3 asymptotes for as long as it can. So it wants to stay right next to it, but then all of a sudden, it can't keep going up. It has to go through that point. and then it curves, and it can't keep heading that way because it hits another asymptote. And it has to curve back down through this bottom one. So it's going to have to look something like that. One thing I'm not sure about is this section up here. I know I have to stay very close to that. And I know that I have to stay pretty close to that. And those two pieces have to connect somehow. Well, if you're not sure how they connect, try 1.5. Get another point. 1.5, I'm at about 8. So let's graph that point. 1.5, 2, 3, 4, 5, 6, 7, 8. It's actually a little above 8. I'm about right there. So I can kind of see what's going to happen here. It's going to come down. It's going to go through that point, and it's going to keep going. These pieces just keep going. And that's what that graph looks like. Right, so let's see if we did an okay job. This piece I can just barely see. That's the top of my standard window, 10. Let's set it to 20. Actually, it's set to 30, so that's good. So we're going to see more of this piece at the top. So there's the piece on the left. There's the piece in the middle. And there's the piece on the right that, again, you're only seeing a very, very small part of in that graph. But that's what it looks like. Any question on how we sketch that? All right, let's just draw this. Okay, so this is one, they just want us to type it in. We don't have to do anything by hand with it. It just says use a calculator to graph it. What's the difference between the degree in the top and the degree in the bottom? 1. So what kind of asymptote would you expect when the difference is a degree 1? What did we call that? What did we call the asymptote in the last problem? This one. Yeah? It's an end behavior asymptote, but it's not a curve. This end behavior asymptote was on a slant. Probably should have I think I wrote it down, but I didn't show you. So the asymptote in example 7, that was called a slant asymptote. This problem is going to have the same type of asymptote because the difference is a 1. It's a slant. All right, let's graph that and see what happens. And I think I remember what happens, but I'm going to have a question for you about it. So 7x cubed plus 7x squared plus 2x. And we're going to divide by x cubed minus x minus 50. Okay, this is beyond what I would have you do by hand, because the numbers are kind of big. There's a lot to it. So that's why we're not graphing this by hand. I just want to see if we can do it on the calculator. So I typed it in. I'm going to do zoom 6. And that's what we get for a picture. That's pretty good. This piece, if you zoom out more, is just going to kind of keep going like this. This piece just keeps going up, and this piece goes that way. Now, is there anything on that graph that you think looks a little suspicious, like we might want to check it out a little closer? Does anybody see something there that we might want to check out a little closer? Yeah. Which one? What do you want to check out more? Above what?
Like the direction of the one above the x-axis.
This one? So it is something about this one. I mean, I can tell you, this just keeps going. I mean, you're just going to see it go like that, and you're just going to see that go like that. That's all that's going to happen if you keep looking up.
Right.
But what else might we want to look at a little closer? Yeah?
You see the axis in there? Like,
Yeah. I'm kind of interested to see what's happening right there. It looks very flat. Well, let's see. Let's set our window to what I just put a box around. -3 to 2 on the x-axis. So -3 to 2 and -1 to 1 on the y-axis. So we're zooming in on that section that looks flat. When we zoom in, did we really gain anything there? I still can't really tell. It just still looks pretty flat. So let's zoom in again. Instead of going from like -1 to 1, let's try -0.1 to 0.1. And I want you to tell me what you think about that section that was flat. Was it flat? Not at all. Not if you zoom in enough and actually look at what's going on. So, if I asked you how many times that crossed the x-axis, and you said, it looks like maybe it's just once. Well, if you zoom in, you can actually see it's 1, 2, 3, 4 times. But you'd never be able to tell that without zooming in enough to see it. So the point is, check out the detail if you need to on a graph by zooming in. All right. So for tonight, again, we're not going to be doing an assignment in the book. Take home.
Everyone's attention regarding.
Okay. So the take home is on school. No, it's not on school. It's on Edulastic. Sorry. It's due at 8 a.m. tomorrow, Eastern Time, October 7th, 2022. It will open in 3 minutes. It's on Edulastic, and you have a little bit longer than normal. We usually end up with about under an hour to take a test. I think it's 11 questions, and you'll have 90 minutes. You don't need to do the whole thing at once. You can pause, come back to it. But if you're going to pause, close the screen. Because if you leave close it out. It'll save it.
So you don't have to pause, you just close it.
Yeah, you just close it out. Because if you leave it open on the screen, the 90 minutes are going to count down.
Makes sense.
Yep. Does anybody have a concern about doing it as a take-home? I don't have Wi-Fi, I don't have a graphing calculator, I don't have a computer. Does anyone have a concern?